Welcome back to the Deep Dive. It is great to have you with us today.
Really glad to be here.
We are embarking on a very specific mission today. We are looking at what it actually takes to make artificial intelligence truly useful for you in your everyday life.
Right, moving beyond the basics.
Exactly. We are talking about taking AI from being just a remarkably articulate chatbot that can, draft a polite email and transforming it into a super-powered digital assistant.
One that actually takes action, right? Pulls levers and pushes buttons in the real world.
Yeah, which is basically the holy grail of current tech development. Everyone wants an AI that doesn't just talk about doing things, but actually goes out and executes them.
And to figure out how we cross that bridge, we are digging into a really fascinating stack of sources today.
We sure are. We have an excerpt from the Gen AI Foundations podcast, which kind of sets the stage on the state-of-the-art generative AI landscape right now.
But the main event, the real core of this, is a dense and honestly groundbreaking research paper.
Yes, titled ToolLLaMA, Facilitating Large Language Models to Master 16,000 plus real-world APIs.
Which comes from a highly dedicated team of researchers at Tsinghua University alongside several other institutions.
It is a monumental piece of work. They are fundamentally addressing how to teach open-source AI models to navigate the wild west of the internet completely independently.
How to use thousands of real-world internet tools.
And why figuring this out is basically the ultimate shortcut to having a highly capable AI assistant that isn't entirely controlled by closed corporate systems.
Which is huge for the end user.
Definitely. Okay, let's unpack this. Let's start with the core problem here. We have these amazing open source language models now, like Llama.
They are fantastic at generating text.
Oh, absolutely incredible at test, but they possess a glaring blind spot, which is tool use.
Right, which is a massive limitation in practice.
Because if you ask a closed proprietary model like ChatGPT or GPT-4 to say, check the weather in Tokyo or find livestock prices or book a flight.
They can just reach out to external APIs.
Yeah, application programming interfaces to fetch that live data.
But out of the box, our best open source models just cannot do that at all.
No. They are effectively trapped in their own text generation bubble. They rely solely on whatever information was baked into them during their initial training.
I like to think of it like teaching someone to be a brilliant, world-class conversationalist, but then locking them in a room without a smartphone or an internet connection.
That is a perfect way to visualize it, and we really need to understand why this gap exists in the first place.
Well, it comes down to how we train these open source models. The process, instruction tuning, has historically been heavily focused on basic language tasks.
Like summarize this article, write a poem, or translate this sentence.
Exactly. The entire domain of actual tool use was largely neglected during that tuning phase.
But, people have tried to fix this before, haven't they?
They have, yeah. But according to our sources, those early attempts fell incredibly short.
Because they were too simple. Way too simple. They used very limited sets of APIs, sometimes just a handful of them. And they often didn't even use real-world RESTful APIs.
Actually, before we go further, for the listener who maybe hasn't built a web application recently, what actually makes an API RESTful and why does that even matter for our AI?
That is a great question. Think of RESTful architecture as the standardized language, the core etiquette of the modern web.
Okay.
So when your weather app asks a server for today's forecast, it uses a RESTful API. It sends a specific type of request, like a GET request, and receives data back in a highly predictable format.
And the older AI training didn't use that?
No, they didn't use this real-world standard at all. They used simulated, simplified toy environments.
Like a sandbox.
Right. And perhaps most critically, those older studies only tested single-tool scenarios. They would tell the AI, use this one specific calculator tool to do this one specific math problem.
Which is completely detached from reality. Real problems require juggling multiple tools, cross-referencing information, adapting on the fly. What's fascinating here is the broader implication for the AI landscape. Right now, sophisticated tool use is effectively locked behind the closed doors of proprietary models.
You can't look under the hood to see how they interact with the web.
Exactly. And if we want true democratization of AI, if we want a future of community-driven innovation where anyone can build incredibly capable systems on their own hardware,
then these open source models absolutely must learn to use tools natively.
we cannot have the internet's intermediaries monopolized by just a few massive tech companies.
Which brings us to the hero of our story today, ToolBench.
Yes.
The researchers at Tsinghua University realized that if the core problem was a lack of high-quality training data, they simply needed to build the ultimate training ground.
And the sheer scale of the solution they came up with is just staggering.
It really is. They did not just grab a few dozen APIs to test. They went to a platform called RapidAPI Hub and collected 16,464 real-world RESTful APIs.
That number really bears repeating, over 16,000 distinct interfaces.
Spanning 49 different categories. We are talking finance, sports, weather, social media, e-commerce, cloud computing, you name it.
It is an immense data set.
But here is the logistical nightmare they faced with that. You cannot hire enough humans to sit down and write out complex, step-by-step reasoning instructions for 16,000 APIs.
No, it would take an army of developers decades to map all that out.
So how do they actually generate the training data?
They used AI to train AI. Specifically, they utilized ChatGPT, the GPT 3.5 turbo model, to generate the entire data set automatically.
Wow.
Yeah, and they structured this into three very distinct stages. First was the API collection stage, where they scraped all that rich documentation from RapidAPI.
Getting all the instruction manuals, essentially.
Second was the instruction generation stage, where they prompted ChatGPT to invent diverse, creative, and highly convoluted tasks that would actually require using combinations of these specific APIs.
And then the third stage.
Third was the solution path annotation stage.
And that third stage is where the methodology gets really wild.
It really does.
Yeah.
In that stage, they essentially forced ChatGPT to play the incredibly complex game it had just invented.
Like solve your own puzzle.
Exactly. They asked it to search for a valid solution path, a sequential chain of actual API calls, to successfully solve the multi-tool instructions it generated in stage 2.
And the instructions it came up with were anything but simple. I have to share a specific, wonderfully bizarre multi-tool instruction generated in the study just to show you how complex this training ground really got.
This is a great example.
Imagine the scenario. A user comes to the AI and says, I want to name my newborn cat after Kobe Bryant, and I want to host a party to celebrate its birth.
Just a completely standard Tuesday on the internet, right?
Exactly, the kind of chaos a digital assistant needs to handle. But the prompt continues. Get me some cat facts and NDA news to gather inspiration for the cat name. Also, find a proper hotel around my house in downtown Houston for the party.
But think about what the AI has to do here.
It has to simultaneously navigate 3 completely disconnected APIs. An NBA News API, a cat facts API, and a hotels API.
And consider the memory management required for that process alone. It has to fetch the cat facts, hold them in its working memory, scan the NBA News for Kobe references, parse that text, and then
execute a geographic search to book a hotel in a specific zip code in downtown Houston.
passing the outputs of one API logically into the parameters of the next one.
And the paper points out a pretty brutal technical hurdle here. When the AI actually calls these real-world APIs, the responses they send back are not neatly formatted little summary sentences.
Oh no, they are colossal blocks of code.
It's just a mess to read.
When you ping a real API, it returns huge JSON files filled with redundant metadata, tracking codes, server statuses, formatting tags.
And the sheer volume of text in these responses is often way too long for an open source model's memory, right? Its context window.
Exactly. The AI would simply crash or forget the first part of the task by the time it read the end of the server response.
So how do you fix that?
To fix this, the researchers had to implement a vital compression step. They used ChatGPT to essentially read the raw API response, strip out all the redundant server garbage, and extract only the critical information.
But even with that compression, the paper mentions they still had to use a technique called positional interpolation, and they used that to artificially extend Llama's context length to 800 and 192 tokens, just so it could hold all the tool data in its head at once.
Yes, that was a crucial architectural tweak.
For someone who hasn't kept up with the latest in language model architecture, what is positional interpolation actually doing here?
Let's break that down simply. Language models are trained to understand a specific length of text, say 4,000 tokens or words.
Okay.
They mathematically assign a position to each word, word 1, word 2, all the way up to word 4,000.
Right.
If you suddenly hand the model word 4001, its brain basically breaks because it doesn't have a mathematical slot for that number.
It just doesn't know where to put it.
Right, so positional interpolation is a very clever mathematical trick. Instead of retraining the whole model from scratch to learn numbers up to 8,000, it squishes the existing numbers down.
Squishes them.
Yeah, so instead of word 1, 2, 3, it treats them as word 0.5, 1.0, 1.5, it artificially stretches the model's short-term memory capacity into the same mathematical space it already understands.
Oh, wow. It's like writing smaller on an index card so you can fit twice as many notes for the final exam.
That's a great analogy.
That is brilliant. But this brings up a massive structural question. How does the AI actually figure out the logical steps to solve these wild multi-tool tasks?
That is the big question.
Because if it is trying to book the Houston hotel and fetch the cat facts simultaneously, how does it not just get totally confused, hit an error, and give up?
That represents the core algorithmic challenge of the entire paper. Up until this research, the standard, widely accepted method for getting an AI to reason through a multi-step problem was called RESTful, reasoning and acting.
We have actually discussed the RESTful framework on the show before, and it sounds great in theory.
The theory is solid. The AI generates a thought, takes an action based on that thought, observes the result from the environment, and then has another thought.
Makes sense.
But the Tsinghua researchers point out that RESTful suffers from a fatal flaw when applied to massive, unforgiving API environments. And that flaw is error propagation.
Meaning one small mistake cascades into total failure.
Precisely. If the AI makes a single tiny error early on, say it formats a date using dashes instead of slashes when asking the hotel API for room availability, the API kicks back an error message.
Naturally.
Under the traditional RESTful framework, the AI lacks the ability to effectively rethink its entire approach. It often just gets trapped in a faulty loop.
So it just keeps trying the wrong date format.
It will continually call the API the exact same wrong way, over and over. Or, in a desperate attempt to move forward, it will start hallucinating fake APIs that don't even exist until it entirely fails the task.
Here's where it gets really interesting, because the research team realized RESTful was never going to cut it for navigating 16,000 unforgiving tools.
Not even close.
So they introduced a major breakthrough reasoning solution. They call it DFSDT.
Depth-first search-based decision tree. I know you were looking at a great analogy to explain the mechanics of this earlier.
Yeah, let's translate this into something visual. Imagine the AI is trying to solve a problem by walking down a long hallway with multiple closed doors.
Okay.
RESTful is like walking blindly down that hallway, hitting a locked door, and just banging your head against the wood over and over until you collapse from exhaustion.
A terribly inefficient way to navigate the world.
Right. But DFSDT, this new decision tree method, turns the AI into a methodical explorer. It allows the AI to evaluate multiple paths simultaneously.
It can look ahead.
Exactly. If it walks down a path and realizes a door is locked, maybe the API server is down, or it used the wrong input parameter, it doesn't just bang its head. DFSDT allows the AI to actively register a command called finish by giving up on that specific branch.
It consciously aborts the bad path.
It literally leaves a mental marker saying, this way is a dead end, backtracks to the main hallway, and tries a completely different door.
And from a mathematical standpoint, this expands the search space exponentially. Instead of a single, fragile chain of thought that breaks at the first sign of trouble, you construct a robust, branching tree of possibilities.
Which changes everything.
The paper's data shows that this DFSDT method empowers the AI to solve complex, difficult instructions that vanilla RESTful could never possibly complete.
And they use this to make the dataset better, too.
Exactly. Because they use this advanced decision tree to generate the training data itself, the resulting ToolBench dataset wasn't just larger in volume, it was exponentially higher in quality. It contained successful, proven paths through incredibly convoluted API mazes.
So we have this vast dataset, and we have this brilliant branching way of navigating it. But let's bring this back to you, the listener, sitting at your laptop.
The practical application?
Yeah. If you are actually deploying this AI in your workflow, you do not want to sit there manually scrolling through a directory of 16,000 APIs to tell the AI which ones it is allowed to use for your specific prompt.
No, absolutely not.
Handpicking API number 4,000 and 12,000 completely defeats the purpose of having an assistant in the first place.
It absolutely defeats the purpose. The system must operate autonomously from the user's perspective. So to solve this practical dilemma, the researchers introduced an entirely separate component called the Neural API Retriever.
The digital matchmaker.
That is exactly its function. It's a specialized model trained using an architecture called SentenceBERT.
Okay, SentenceBERT.
Its singular job is to read the user's plain English prompt. For example, help me plan a movie night in the mountains. And then it automatically sifts through the 16,464 APIs to recommend the absolute best tools for that specific job.
Wait, let's clarify sentence spurt real quick, because normally if I search a database for movie night, a basic search engine just looks for the word movie. What makes this neural retriever different?
The difference is keyword matching versus semantic understanding.
Semantic understanding.
Right. A basic keyword search looks for exact text strings. But SentenceBird is a natural language processing model that maps entire sentences into a mathematical space based on their meaning.
Meaning not just the letters.
It understands that a prompt asking for film viewing or cinema is conceptually identical to movie. It matches the underlying intent of the user's prompt to the descriptive capabilities of the APIs, rather than just looking for matching words.
So it's like a librarian who instantly knows which 3 books out of a colossal library you need just by listening to you describe the vibe of the research you're doing.
That's it, perfectly.
And the researchers tested this retriever, and there is a massive, surprising twist in their findings. Wait, don't tell me the AI librarian actually beat the human researchers at their own game.
I love how excited you get about this stuff, but yes, it absolutely did.
That is incredible. Walk us through that test.
Well, they set up a comparative evaluation. First, they gave the model the exact, perfect ground truth APIs.
The ones the humans picked.
Right. These were the tools the human researchers had meticulously curated and knew were the mathematically correct tools for the generated task.
Okay.
Then they ran the test a second time. But this time, they withheld the human answers and let the neural API retriever autonomously recommend the tools.
And the result?
The result was totally counterintuitive. The model actually outperformed the human-curated ground truth when it relied on the retriever.
You would naturally assume the human-provided, mathematically verified correct APIs would set the ceiling for the highest possible score. Why on earth did the AI do better?
Because the retriever found better alternative APIs buried deep in that massive database.
It found better tools.
It discovered tools with broader functionalities or more stable servers that the researchers themselves hadn't even considered or realized were available.
So the AI librarian knew the library better than the architects who built it. It found a more efficient way to solve the problem simply by cross-referencing capabilities at a scale humans cannot manage. It shows the AI is moving from just being a tool user to being an active tool evaluator.
It proves the system isn't merely memorizing static routes. It is dynamically evaluating utility in real time. But that revelation actually brings us to a monumental logistical problem the researchers faced. The grading process.
Oh, of course. How do you possibly grade a test when there is an infinite number of correct paths to the answer?
It's a daunting challenge. If you have a sandbox of 16,000 APIs, there might be 100 slightly different ways to successfully book that Houston hotel and find those Kobe Bryant cat facts.
Right.
Human annotators simply cannot grade this efficiently. It would take an entire department of engineers months just to manually evaluate one model's performance on a few thousand tasks.
So, to solve this grading nightmare, they built ToolEval.
Yes.
It is an automatic evaluator, again backed by the reasoning power of ChatGPT, and it effectively acts as the judge, jury, and scorekeeper.
And ToolEval measures 2 distinct metrics.
First, the pass rate. Like, did the AI actually complete the user's instruction without crashing, erroring out, or hallucinating data? Fundamentally, did the solution actually work?
Right. And second, the win rate.
The win rate.
Yeah. If you pit 2 AI models against each other on the exact same task, which one engineered a better, faster, or more elegant method to arrive at the solution?
And naturally, any skeptic would wonder, can we realistically trust an AI to accurately grade another AI's complex code execution?
It's a valid concern. But the researchers investigated this thoroughly. They had human experts blindly grade a subset of the API results, and they found that ToolEval's automated grading correlated 87.1% with human evaluators.
Wow, 87%.
That is a remarkably high level of agreement, confirming that ToolEval is a robust, scalable methodology to assess these models objectively.
So the stage is entirely set. We have the staggering ToolBench training data, the DFSDT decision tree for reasoning, the neural retriever for matchmaking, and the automatic grader to measure success.
All the pieces are in place.
The Tsinghua team took all of these components and they fine-tuned the open-source Llama 2 model. The final product is what they named ToolLLaMA.
And the benchmark results are, well, they are a bloodbath for the competition.
The performance metrics are undeniable. When you equip ToolLLaMA with that DFSDT reasoning, the ability to backtrack out of the locked hallway doors, it confidently surpassed closed-source models like Anthropic's Claude 2 and OpenAI's Text DaVinci 0.003.
It even performed almost on par with the teacher model itself, ChatGPT.
Think about the significance of that. An open source model running locally on independent hardware, rivaling the capabilities of a multi-billion-dollar proprietary system.
It's incredible. But looking closely at the data, the most revealing part of the evaluation wasn't who ToolLLaMA beat.
No.
The most profound insight came from the control group, the spectacular failures.
Oh, the models that scored zeros across the board.
Correct. They tested two other incredibly popular, highly respected open-source llama variants, Vicuna and Alpaca.
Which are great models.
Fantastic at their jobs. But they were fine-tuned purely for general dialogue and following standard text instructions. When put through the ToolEval gauntlet and asked to navigate real APIs, they scored a 0.0% pass rate.
0.0. They failed every single task. They didn't even stumble into a correct answer by sheer luck.
Not even once.
So what does this all mean?
It definitively proves a crucial theory currently debated in machine learning. Instruction following in language does not automatically equate to tool use capability.
It's a completely different skill.
Just because an AI model can write a brilliant, nuanced essay or summarize a complex legal document flawlessly does not mean it possesses any inherent understanding of how to interact with a digital environment.
Right.
Tool use is an entirely separate cognitive skill, computationally speaking. It requires understanding syntax, error handling, sequential logic.
Right.
And it must be explicitly taught.
You cannot just assume the brilliant conversationalist intuitively knows how to drive the car. You actually have to put them behind the wheel and give them driving lessons.
Exactly.
Which brings us to the ultimate final test for ToolLLaMA. It is one thing to memorize the 16,000 APIs you were specifically trained on, but the internet is a living ecosystem. It changes every single day.
It does.
What happens when the AI encounters an interface it has never seen before?
Well, in machine learning, this is referred to as out-of-distribution testing. It means evaluating the model on data sets it has never, ever encountered during its training phase.
The ultimate blind test.
To execute this, the researchers utilized a completely different dataset called API-Bench. This dataset contains APIs from highly technical, specialized platforms like TorchHub, TensorHub, and Hugging Face.
Deeply nerdy, complex machine learning APIs that are far removed from booking a hotel or checking the weather.
Very far removed. And ToolLLaMA had zero exposure to these APIs during its development. Yet, because it had been trained so rigorously on the underlying principles of how to read documentation and how to navigate tool logic via that decision tree, it did not stumble. ToolLLaMA figured out how to use these unseen APIs simply by reading their documentation on the fly and adapting its approach.
It read the instruction manual for a foreign machine and just operated it perfectly.
Furthermore, it actually performed on par with, and in several metrics defeated, a different AI pipeline called Gorilla.
And Gorilla was trained on that specific data, right?
Yes. Gorilla is a specialized AI that was explicitly trained on that very API-Bench dataset. ToolLLaMA beat the home team on their own turf without ever practicing there.
That is wild.
If we connect this to the bigger picture, consider why this adaptability matters so deeply for you, the listener. Let's say your company uses a completely proprietary, custom-built internal inventory API.
Something totally unique to your business.
It lives on a private server. It is not on the public internet. ChatGPT has never seen it and cannot access it.
Right.
If you deploy an open-source model possessing the generalized capabilities of ToolLLaMA, you can hand this AI your brand new, customized API documentation tomorrow morning, and it will inherently know how to interact with it.
That's a game changer.
You avoid spending millions of dollars and months of time retraining a model from scratch. The AI already understands the fundamental philosophy of tool use.
It transforms the AI from a static read-only database of historical knowledge into a dynamic, adaptable engine of real-time action.
The transition from passive observer to active participant.
It really is a monumental leap forward for open-source technology. We began this deep dive discussing the vast gap between generating articulate text and actually taking meaningful action.
Yes, the action gap.
What this rigorous research from Tsinghua University demonstrates is that the gap is closing much faster than anticipated, thanks to brilliant architectural innovations like depth-first search reasoning trees and impossibly rich training datasets generated by utilizing AI to teach AI. Open-source models are finally waking up to the real world.
They are learning the intricate language of the web, pulling the levers and pushing the buttons of the internet infrastructure.
And for us, as individuals navigating an increasingly complex digital landscape, this is how we survive information overload. This is how we avoid being completely locked into the walled gardens of tech
By
monopolies.
having our own systems.
Exactly. By fostering capable open source intermediaries, digital assistants, we can actually own, audit, and control that can sift through tens of thousands of applications, execute the mundane tasks, cross-reference the data, and take action on our behalf.
It provides an incredible level of technological empowerment. However, studying the rapid trajectory of this development presents a fascinating next step to consider. A final thought for you to chew on today as we wrap up.
I love a good final thought. Let's hear it.
We have just explored how an open-source AI can master 16,000 human-made APIs simply by reading the documentation and dynamically backtracking through different logical paths.
Right.
But remember, human-made APIs are built specifically for human developers to read, understand, and debug. They are inherently bloated with explanations, they are computationally slow.
Like those massive, heavy JSON data files full of formatting tags we talked about earlier.
Exactly. They are inefficient for a machine operating at lightning speed. So, the inevitable question becomes, what happens when these incredibly capable AI models realize that human-made APIs are acting as a bottleneck?
Oh, wow.
What happens when, to optimize their own internal processes, these AI assistants stop reading our documentation and start writing and executing their own custom APIs?
Building their own tools.
Interfaces built in hyper-compressed languages and formats we don't even possess the capacity to understand, functioning purely to allow machines to communicate with other machines instantaneously.
A completely invisible machine-to-machine internet evolving and operating right under our noses at speeds we can't even perceive. That is an incredibly wild, profound thought to end on. Thank you so much for joining us on this deep dive into the expanding capabilities of open source AI. Keep questioning the tools you use, keep exploring the technology around you, and we will see you next time.